Good morning and welcome to the Rosenberg International Forum on Water Policy's first virtual event series for this year. This is the first of three. This one is on the state of climate and impact on extreme weather. Just a brief update about how you can participate today. If you have questions, they'll be answered by the presenters with the help of the moderator, Ariel Dinar, during the Q&A period at 9:10. If you have questions that come up before then, please do type them into Zoom's chat and we'll be keeping track of them and the moderator will read it for you. Alternatively, you can raise your hand during the Q&A period and you can unmute yourself when we call on you and you can ask your question live. Please do keep questions pointed. Any comments or observations, please type into the chat throughout.
All right, well, good morning, good afternoon, good evening, depending upon where you are on our planet. Thank you for joining us for the second year of our webinars on the Rosenberg International Forum, which traditionally was a biannual meeting face-to-face, which unfortunately was not possible. However, we are very delighted to really organize these three webinars a year, which are really focused on special topics. And this one, of course, is the state of climate and impact of extreme weather with three incredible and distinguished colleagues, which will be introduced in a few minutes. I'm Soroush Sarushian from the University of California here in Irvine and the current chair of the Rosenberg Forum. Without any further delay, I will ask my colleague and Vice President of the University of California System on Agriculture and Natural Resources, Dr. Glenda Humiston, to say a few words before we move on with the program. Glenda?
Thank you. As Soroush said, I'm Dr. Glenda Humiston. I'm the Vice President of Agriculture and Natural Resources for the University of California System. We're extremely proud to be able to offer these webinars to you as part of our Rosenberg International Forum on Water Policy. This forum originated in 1996 thanks to a very generous gift of the then bank chair and chief executive officer of the Bank of America, Richard Rosenberg. He was a long-time leader in water resources and credited with rallying the California community, north, south, east, west, urban, rural, into trying to identify causes and impacts of the major drought back in 1987 to 92 that we experienced here in California. And he saw the need to really dig into these issues. The forum itself is normally held every other year in different locations around the planet. We limit participation to about 40 to 50 scholars where we can really dig into and discuss these issues around the science of water management, different experiences, and how countries and regions around the world are managing water resources, and then try to come up with some ideas, some solutions that we can share. With the impact of COVID, getting together face-to-face was not possible right now. So we are offering this series of webinars to keep in touch with our alumni, as well as welcome new water experts and policy big thinkers in the water arena to us. So with that, let me thank all of you for joining us today. We have some great speakers. We're looking forward to hearing from them. And I will turn it back to Dr. Sarushian, the current director of our Rosenberg Forum, to introduce our speakers and get us through the agenda. Thanks, Soroush.
Thank you, Dr. Humiston. I appreciate that. And without any further delay, it's important for me to also introduce the members of our advisory board. And the best way is maybe to have each of them to say a word about themselves. I'll start with Christina.
Hello, everyone. It's very nice to be here today. Thanks for taking the time to join. My name is Christina Babbitt, and I work for Environmental Defense Fund, managing our California groundwater program. It's nice to see you all.
Thank you, Christina. And Christina has put together our third webinar to be in February on groundwater issues. And I hope that you can join us then. Lucia De Stefano is our other board member. Maybe there is a connection issue, but let me move to Dr. Ariel Dinar.
Good morning, good evening, everyone. My name is Ariel Dinar. I am faculty with the School of Public Policy, University of California, Riverside, and I'm glad that all of us are here today.
Thank you. And next is Chunwan Duan, who will moderate the meeting today.
Yeah, good morning, good afternoon, good evening, depending on where you are. I'm Qingyong Duan from Huahai University in Nanjing. I'm a hydrologist. I had a fortune working with one of this in the agency, National Weather Service, many years ago. Dr. Mussolini, we are going to be the speaker. So I used to work in that agency.
So let's go to Alberto Garrido. Alberto.
Hello, good morning, good afternoon here in Europe. My name is Alberto Garrido. I'm a professor of agricultural natural resource economics at the Universidad Politécnica de Madrid, Technical University of Madrid. And I've been serving in the advisory board since its beginning in 1996. And my area of work is related to water economics, water policy, and water law, specialized in water markets, prices, and more recently on climate change and agriculture. Thank you very much. I'm very pleased to be in this seminar.
Thank you, Alberto. And Dr. Andrea Gerlach.
Hello, I'm Andrea Gerlach, and I'm on the faculty at the University of Arizona in the School of Geography, Development, and the Environment, and with the Udall Center for Studies in Public Policy. Welcome, glad you're with us today.
And again, Andrea has been kind enough to organize our second webinar, which will be sometimes in early December, I think. And it's on the topic of COVID and its impact on the water infrastructure and everything else that goes with it. Should be very exciting. Dr. Helen Ingram.
Hello, everybody. I'm Helen Ingram, and I'm a longtime member of the executive committee. And it's been one of the great joys of my life. This has been a very successful enterprise, and I'm so glad to join you today, and I welcome you to what I think will be a wonderful webinar.
Thank you, Helen, and I owe a lot to Helen. When I joined the University of Arizona as a young faculty, Helen was a senior faculty there and certainly mentored me along the way, and I'm grateful to her. Ben Maddox.
Good morning, all. Thank you very much for having me. I am the Western Food, Ag, and Wine Executive for Bank of America, based in the central part of California, covering the western 11 states in the U.S. So it's a privilege to be on this committee. I just joined first part of this year, and really looking forward to seeing where it goes. So thank you, Suresh. Appreciate it.
Thank you, Ben. We appreciate your participation. I'm not so sure. Was Ayman able to join us?
Not yet.
Not yet. So we will wait, and if he joins later, we'll introduce him. Ayman is a hydrologist and also a long-term member of the advisory board before my time, and he's in the Palestinian hydrologic group in Palestine. The ex officios that are, of course, critical and pivotal to the success of this entity. Dr. Glenda Humiston already introduced herself. Unless she wants to say something more, otherwise I'll go to Dr. Doug Parker.
Hi, everyone. Great to be here this morning in California and see so many faces from across the world. I'm Doug Parker. I'm the director of the California Institute for Water Resources at UC Ag and Natural Resources, and I'm an ex officio member since the Rosenberg Forum is part of our Water Institute program. And I'm a water resource economist by training.
Thank you, Doug. And of course, no program will be really successful without really having incredible staff. And Sherry Cooper, whom I'm sure everybody knows because she's interacted with you. Sherry, you want to say something about yourself and maybe introduce your colleagues?
Sure. Thank you, Suresh. So I'm Sherry Cooper. I'm officially an employee of the UC Agriculture and Natural Resources Program Support Unit. And I also am the admin officer for the International Rosenberg Forum. My staff, Rachel Palmer, is here to assist, and Clint Zhu will also be assisting. So no program, I couldn't do what I do without them. So I really appreciate them. Thank you, Sarush.
Thank you. And I guess at this point, I will turn the meeting to Duan to start introduction of our speakers. And I hope everyone will enjoy as much as I expect to enjoy the webinar today. Thank you. Yoon?
Yes, it's a pleasure, to host this webinar on today's topic, the state of climate and its impact on extreme weather. I think it's a very timely topic for this year. This year we see all the different kinds of extreme events happening all over the world. Talk about floods, like in China. Last month in Zhengzhou, we have like one day precipitation exceeding 600 millimeters. And we know like Germany and US, like the Hurricane Ida, caused all those subway to be flooded in New York. So, and also heat waves, like in Canada, in northwestern US, you see temperature goes up to like more than 45 degrees, and with many people suffering, actually, a lot of economic losses. So also this year we have the publication of the sixth report of the IPCC assessment report. And so this topic, so I'm sure a lot of people are very much interested. We have a distinguished panel, three distinguished speakers are going to speak on this related to the climate extremes and how we deal with, how we cope with these extreme events. So the first speaker, I think we will introduce each speaker when they speak. So the first speaker is going to be Dr. Pandora Hope. He is going to talk about a net of drought and flooding rains, forecast impact, causes of recent extreme across Australia. But actually, I forgot to introduce her. Dr. Hope actually is a principal research scientist at Australia Bureau of Meteorology. She actually is a lead author for the report I just mentioned, the sixth IPCC assessment report. And so without further ado, I'm going to turn over to Dr. Pandora Hope. So it's your platform. Right?
Thank you. It's an honor to be invited to come and speak to you. For the last 20 years or so, as an atmospheric scientist, I've looked to understand why we're seeing the rainfall declines that we're seeing in Southern Australia. And it is an honor to come and share some of the findings that we've had across my team and my institution. So I work at the Bureau of Meteorology, which is an operational institution. We put out seasonal forecasts, but I'm in the research section and very much interested in what's driving these changes in our droughts and our floods. So I think at the end of this, we might end up with more questions than we have answers, but I think that's always a good thing in a academic world. So just to set the scene a little bit, these are projections of rainfall at varying levels of global temperature going forward in time with warming. And you can see in some regions there are increases in rainfall, but in subtropical southern hemisphere regions, there's decreases right across the area. And in Australia particularly, we see this strong decrease in the southwest and all up the east coast here. So this is the sort of background that we've got in our minds as we think about our changing variability of rainfall. I'm going to focus particularly on Eastern Australia, the Murray-Darling Basin, which is our big river system in Australia that provides a lot of the water resources and agricultural regions for the whole country. Australia is really a very dry place, so a lot of the time it's very water limited. So perhaps if you go forward with that in your mind, you might have a sense of where a lot of this discussion is coming from. So looking at the last 120 years of rainfall, to really focus our minds, I'm actually going to look at just the last 5 years, which has seen 2 extreme flooding events, as well as these 3 years of very low rainfall that ended up with the extreme fires we saw at the end of 2019 and the start of 2020. Those 3 very dry years also happen to be the warmest years on record, and that's obviously another aspect that we have in our climate that's influencing our water resources and the evaporative demand from our land surface. So if we focus in on those 5 years of rainfall, this is the monthly time series starting in January 2016. And we can see this period here, September 2016, there was record rainfall right across the Murray-Darling Basin. Moving forward in time, we had 3 years with record low rainfall, culminating, as I said, in those fires at the end of 2019. And then coming out of that, we had drought-breaking rains here, but then major floods in March of 2021, this year. So they are the 3 features I'm going to focus on and have a think about what's driving those particular events, and is climate change influencing them, and in what way? So if we think first about that extreme September rainfall in 2016, this is a paper with some colleagues where we really had to think about what was driving this, record rainfall in September. It really stood out. It had widespread impacts right across the basin. You can see there, wettest on record in many regions in the southern part of the basin, and that had much flooding and impacts on agriculture. So we have a system that we use for our attribution where we actually run a seasonal forecast of that record event. So it's a sub-seasonal forecast just for the September in 2016. And in the red is how it was forecast in the present climate, with the ensemble spread marked with this red bar. And we also rerun the experiment, but with the background warming that we've seen due to climate change removed from the system. So it's a coupled atmosphere-ocean dynamical forecast model, and we remove an estimate of the changes that we might have seen in the atmosphere and the ocean, and then we rerun the forecast. And interestingly, we see that actually there was minimal effect from climate change. If anything, it was driving drier conditions. So what was driving that extreme? If we look back in time, that signature is actually relatively consistent across most Septembers over the past 15 years, where we're seeing a bit of a drying influence from climate change on this 1 month timescale. With the system, we can actually look at a whole range of variables, and we started to look at the breakdown of what we need to actually bring a heavy rainfall event. Obviously, you need a lot of moisture in the air, so the total column precipitable water, and that was very high in September 2016. These are the observed anomalies here. We also need uplift, so some trigger to actually make that moisture in the air come out and rain. And we did see that as well with this very high negative, means high buoyancy frequency, which shows you that instability of the air, which would encourage rainfall. With our system, this is that precipitable water observed anomaly again. And we can see that in the present climate, we have more precipitable water right through the tropics, as we expect in a warming climate. But interestingly, in the subtropics, as you might have guessed perhaps from that trend in the mean rainfall, we're actually seeing less. And that's in 2016 and in the climatology. And so obviously, even though we think of warmer temperatures, more moisture in the air, there actually needs to be circulation that's conducive to transporting that moisture into your region if you're in the subtropics. Turning to that buoyancy frequency, that trigger for rainfall, and we can see a similar signature that this yellow means that we're actually becoming more stable through the atmosphere. And in the climatology, that's a consistent signature right across the region, that with this global warming we've seen so far, we're actually seeing a shift to a more stable atmosphere, which will make it harder to trigger extreme events like this. So what was going on? One thing that, looking at the results from the IPCC, it's really interesting that if we look at the annual maximum daily precipitation with different levels of global warming, 1.5, 2, and 4, you can see in most regions, we do expect an increase in this one-day precipitation. So perhaps it's worth looking more deeply and not just at the monthly timescale, but at the daily timescale of what processes might have been driving that extreme. If we think about this contribution from the warming, we see that that is driving increases in moisture availability everywhere, but it's that circulation change that's really pushing against that. And so we're not seeing that drive to the extremes that we might expect. But I do want to have a look on a shorter time scale. As I said, we've still got more more questions to explore. So following that very wet period in September in 2016, which would have led to growth. So in Australia, as I said, we're water limited. So when it rains, things grow. Through the forests and undergrowth, we would have had growth right through that region. We then moved into this extended period of drought, 3 years of very low rainfall. And I'll just touch on that a little bit here. So that was the lowest on record in many regions for that 3-year period. And 2019 particularly was very extreme in terms of how dry it was. And it was also the warmest year on record. And that led to the fires. So we think about the antecedent conditions as you come into fires. And obviously, if you've got dry landscape, dry fuel, it's more likely that if you get the right weather conditions and some kind of initiation, you're going to get fires. And we had very, as you know, terrible fires through the end of 2019 and the start of 2020. These are 2 fires that we examined in more detail to try and understand how much of those antecedent conditions influence not just the dry fuel, but also the the live fuel. At the same time, I find these outputs from my department very interesting. At the same time as the fires in Australia, there were also droughts right across the subtropical regions of the Southern Hemisphere, indicating kind of larger drivers were at play. So if we look at those antecedent conditions coming in, this is an estimate from satellites of the live fuel moisture content. So do trees and plants actually dry out even if they're still alive? This is from July in 2019, coming up to the eventual fire in Orroral Valley in late January here. This in the red is the 2019-20 conditions, and you can see that there was just this continual decline in that fuel moisture content. Coming into the fire, it was then the lowest on record, indicating that if you're going to have these extreme events, we actually do have some suggestion of the time frame of warning that we might have. Looking at our land surface models and our water balance models, the top one is a joules-based land surface model, and the bottom one is a water balance model we call the Australian Water Resource Assessment Model. And we can still see that same signature coming from July through 2019 of small increases with small rain events in the surface layer. But as you come down further into the column, you can see that it's really this very significant decline coming into the fire, linking in with that live fuel moisture deficit. Looking at various features, we can actually get an indicator if we look at the deciles of the lead in from spring, the preceding winter and spring, and the preceding 2 years. As I said, it was 3 years of drought. So how much did that impact on the eventual fires? The precipitation was the lowest on record. If we look at these deciles over here, it was in decile 1. Temperature was also very high. The water vapor, in the air was also very low. The live fuel moisture was the lowest on record, as we were saying, in the preceding spring. And the soil moisture through these various measures was also very low. So these indicators, I think, give us a real estimate of that link between the land surface and the eventual extremes that we might see. The forecasts through spring were very good. In the green, we see that spring is a time in Australia that we can forecast very well, and temperatures were forecast to be very high, maximum temperatures, and rainfall very low, which gave fire agencies and our communication, our national broadcasting network, excellent lead-in time for preparing, but it was still a really, really extreme event that we just couldn't prepare for on some levels. So those long-term changes, these are the deciles of the last 20 years for the cool season, April to October. And you can see in the orange there, it's been the driest period on record in the last 120 years of record that we have. Driving that is some work by a colleague of mine, Surendra Ranier and Scott Power. And they've seen that in the climate models, if you force with only greenhouse gases, we absolutely see this decline in the rainfall coming into the recent period in the southeast of Australia. So there's definitely a signal there. And so that might continue going forward in time. But we might also look to the other indicators. So what was El Nino doing at the time? If we look at these Pacific indicators, or those from the Indian Ocean in Australia for the southeast, are strongly influenced by the Indian Ocean dipole. At the time, we also had a significant stratospheric vortex breakdown over the pole and over Antarctica, and that was actually linked to increasing temperature and strong westerly winds coming over the dry continent into the region. The trend has seen this decrease in rainfall in the far southeast, but also an increase in temperature. And together we could build this estimate of what was going on in the spring into the December of the fires. You know, the temperature and the rainfall, but also in this fire danger index, which is based on weather features. The particular driver of importance was the Indian Ocean dipole, and that was found in several other attribution efforts looking at the fire and the influences on it. This is another effort by another one of my colleagues, Han Nguyen, looking to reconstruct the evaporative stress index as we went into one of the days in early January, just preceding one of those fires in the valleys there. And you can see that actually this negative SAM linked to that sudden stratospheric vortex breakdown was very important in driving the East Coast signal. And we can reconstruct quite a bit of the signature of the change, but the trend wasn't so important in this instance, but obviously we have that background that's going to bring us warmer temperatures and long-term drying as a background signature. So moving forward, in February of 2020, we had drought-breaking rains, but there were not significant floods. And then over time, we had a few more months with rainfall, and then this significant event in March 2021, which led to huge flooding a great deal of infrastructure loss and some loss of human life, sadly. But the big factor was the antecedent moisture. So although, yes, it was the wettest on record in some regions, if we have a look at the soil moisture in the month preceding, on the left, we have coming out of the fires into January, into February, where we had that rainfall I pointed out first, but the soils were very dry. Whereas in February in 2021, we had a year of good rains through 2020, and we had these significant floods right through March 2021. So in Australia, I guess, we seem to be having this increasing risk of droughts and floods, but there's still a lot more work to do to actually pinpoint the key drivers and the timescales that those drivers are happening on. And then the antecedent conditions, of course, are real key to the extremes across Australia. Thank you.
All right. So thank you very much, Dr. Hope. It's a great talk. And we are going to have a discussion session at 9:10 the Pacific time. And but if anybody has a kind of a clarification kind of question, we can ask now, if there is any. Seems like seems like no clarification kind of question right now. So thank you very much. We are going to have again, encourage all the people who have questions to put your question in the chat box, and so we are going to ask the speaker to answer them when we have the discussion session later. Now let's introduce our second speaker, Dr. Luis Uccellini, who is the director of the U.S. National Weather Service. He has, of course, a distinguished career, and he said that he's going to retire in January. But under his leadership, the National Weather Service has gone this 10-year, I would say, service improvement. And so he is going to give this talk is building a weather and water regulation, a 10-year perspective, looking back at the accomplishment and forward to the opportunity that's ahead. So welcome, Dr. Uccellini, and so it's your platform. Okay, please take over.
Well, thank you. We'll get the slides set up here. So so what I'll be speaking to is our now almost decade-long effort to build a weather-ready nation, and we'll define that as we get into this talk. So let's go to the outline, please. So what we'll do here is very briefly show what the Weather Service does, what we do, what the Weather Ready Nation initiative is, and what we're introducing here is impact-based decision support services that take us beyond the forecast and warnings to actively connected decision-making at every level of government. And that's what IDSS is all about. This is a big change in our operations. So what does it look like? What does successful IDSS look like? We'll get into that. Some ongoing efforts with respect to social equity, and 2 slides on the water program. This is for Sarush. And then the summary. So I always start with the mission, providing weather, water, and climate data, forecasts, and warnings for the protection of life and property, enhancement of the national economy. It's sort of a 2-part mission statement. And what we've found over this 10-year period, that by working towards this vision of a weather-ready nation where society is prepared for and responds to extreme weather, water, and climate events, where communities are ready, responsive, and resilient through the provision of IDSS, that IDSS is critical for linking the first part of our mission statement of providing to the second part of saving lives and property. We have to do this, not just to realize a vision, but to realize our mission. Next slide, please. And that mission involves about a third of the Northern Hemisphere. So all the way from, I say, from Guam to Puerto Rico, from the Western Pacific all the way to the Eastern Atlantic, from Alaska, Northern Alaska, all the way down to the Caribbean area. So, so we apply that mission in this effort to build Weather Ready Nation over about a third now of the Northern Hemisphere. Next, please. And that domain space is pretty large when you think about the vertical as well. We have forecast responsibility now all the way from space weather down to the surface of the ocean. So what we say is the sun to the sea. And when I talk to students, if I tell them if they're not interested in this domain space, they're at the wrong talk. Okay, so we have this broad interaction, and especially with respect to climate, weather, and water. And we now talk about the weather, water, climate linkage as being a foundation for advancing our weather services. Next slide, please. So what's a Weather Ready Nation? Weather Ready Nation, go to the next slide, please. Weather Ready Nation is a nation that is a ready, responsive, and resilient. This is an outcome. It wasn't a goal based on meteorology or hydrology or climate. It's a societal outcome. It's about becoming a nation that is building community resilience in the face of our increasing vulnerability to extreme weather, water, and climate events. We touch every county in the United States and its surrounding territories every day, right? So this is really, really important that we get this large embrace of the effort that we've undertaken. We do this by supporting national security, public safety through these impact-based decision support services provided essentially to emergency management partners, but also increasingly to our water resource managers as well. And this cuts across all scales, from range all the way to the long-range planning and execution of steps that are needed. Next, please. So IDSS, what's this, right? I mean, I've talked about it now. So this is taking our forecasts and warnings, providing the best forecast in the world. And this involves not just the models, by the way. It goes all the way through the human factor, the forecasters themselves, connected to the decision-making process, right? And we do that by working with these emergency managers, water resource managers, well before an event. We systematically work with them. We have to establish relations. We have to know their needs. We have to practice with them. We have to review past events. What do we do right? What do we do wrong? What can we do better? Okay. We work together as equal partners in this whole endeavor. We had 11,000 ambassadors. Those are organizations cut across nonprofits, government, the works, because it takes the whole community then to get the desired results. The whole thing is based on a trusted relationship across all government levels. So we talk about serving the intragovernmental levels, local, state, federal, especially the locals who make 95% of the decisions in our country for public safety. Okay, so we need that whole spectrum. Next, please. So, you know, different ways of measuring progress. I say there are going to be dozens of PhDs just in terms of how to measure success, because when you do IDSS, you got physical and social sciences. You got human factors, changing risk preferences, the whole works. So how you measure success is a really interesting problem. So what we'll do here is I'll take some of the quotes from some of the top emergency managers in the country, Eric Wagi, and they've allowed me to use these quotes, by the way. They use them at conferences, emergency management and meteorological conferences. So we have revolutionized the emergency management community because they were very reactive, and you can't react to these events. You have to be proactively prepared, and they're seeing results. Furthermore, on the right-hand side, that emphasis on the local presence. We do work with the federal and the state, but we have to be there for the locals who are making the decisions to evacuate, to establish shelters, et cetera, et cetera. It's not a nice to have, as he said, it's an absolute necessity. So that gets us across that whole intergovernmental level of providing our products and services. And that has a very important aspect. They have to be consistent as well as accurate. Okay, no shopping around when you're trying to prepare for one of these events. Next, please. So I got a couple examples here. This is one of my favorite one. This is from 2015 because it involved tornadoes, blizzards, and flooding. And it was over a Christmas vacation. So folks had to come in before Christmas. Remember, it was practice, practice, practice. We start working these events like a week in advance now, right, to alert based on an ensemble model output, essentially. So in this case, you see a whole range of local, when you look at the tornadoes, blizzards, local, state type events or preparations. And then you start seeing the federal come in as well, with FEMA being a part of this. They actually pre-position assets to help the states and locals mitigate these major storms. Well, we had the tornadoes and blizzards. We also had flooding, and this, systematic flooding, flash flooding, systematic flooding over a very large area of the United States. So, we had this difference, and it was an eye opener for us at the beginning of our journey on this Weather Ready Nation. If you go to the next slide, please, I'll show you why with respect to flooding. With weather, you have preparations, and you have maybe 5, 4, 3, 2, 1 day in terms of the tick-tock towards the extreme event. For flooding, it goes on for a long time, and it's exhausting, and you cover different states in a sequential manner. So even though this happened over Christmas, a month later, we still do an IDSS for this flood that's now approaching New Orleans, based on all the rain and the like, and the melting snows up along the Mississippi and Ohio River basins. So there are differences in the IDSS depending on what you're working towards here. All right, next slide, please. Again, testimonials, but this is Governor of Missouri doing his press conference post-mortem at the forecast office in St. Louis. And what he's pointing to in those comments, and I'll leave these slides behind, by the way, anybody can use them, is the IDSS. He's referring to the IDSS that got these folks prepared right down to the local communities across his state. This was true in the other states as well. He just articulated it. So this is something that really started lighting us up and started lighting up the community. This case was sort of a showcase for what was possible. Still a lot of work to do. And even today, as you see in New York City with that flood, we have a lot of work to do. Next slide, please. So here's some visualization. 2013 storm. This one just as I was becoming the director of the Weather Service. Well forecast. Not much connection with decision making, and the public, had to be convinced they had to see something before they went out. Well, those cars that got stuck on the Long Island Expressway took 3 days to remove. 3 days. 2016, 2.5 feet of snow, wind-blown snow. They closed that road down just as it started snowing. Kept the cars off. 18 hours to open up the Long Island Expressway. All right, and besides, states that did not react in 2013 and even in 2016, they had same kind of situations where people's lives are at risk when you're stuck out there in these types of snowstorms. Okay, next slide, please. Another comparison at the city level. The Long Island Expressway, that was decided by the state of New York in 2016. Note the difference between a 2010 snowstorm, blizzard, over the Christmas holiday, where the city of New York decided not to mobilize. 4 days to open up New York City. 2016 had everybody off the road. Okay. Next slide, please. And again, a much faster, recovery. All right, severe weather. Here's severe weather outbreak from 2019 Memorial Day holiday. And this is a listing of the kinds of things we were doing leading up to. We got an outlook from Storm Prediction Center. Then we get into the watch mode as you get into hours before. Then you get into warnings from the local forecast office, which is minutes before, like 20. Hopefully you can get out to 20 minutes. But the fact is, during each one of these steps, there's an incredible amount of IDSS being provided at the federal state. We're getting people prepared. And these folks did get prepared. They were ready for this. In fact, they closed schools early. It was ahead of a holiday weekend. They cleared roads, and they had this F4 tornado. Okay, hit the next click, please. So IDSS was provided during this entire period, 6 days before a severe weather outbreak. Next, please. No fatalities. And if you think this is just a lucky break on one storm, go to the next slide, please. This outbreak actually lasted over the weekend. This is the headline from the Washington Post. And anybody who's visited the United States knows that the Washington Post usually just gives us headlines when we mess up, right? 434 tornado reports, only one fatality in the whole weekend. And that was a midnight tornado, late at night, okay? Incredible, incredible performance. Next slide, please. So let's look at hurricanes. 1999, this is Floyd. Great forecast, make that turn up the coast. Problem was, the emergency management community didn't have a trusted relationship with us. They didn't really believe it. So they evacuated everybody, evacuated them at the same time, and had this catastrophic traffic jam. If that storm had hit either northern Florida, Georgia, or South Carolina with those traffic jams, there would have been a large loss of life. Okay, now let's look at Dorian. Next slide, please. So this 2019, similar track. We forecast the stall over the Bahamas and then the move up towards the coast. So what impact did this have on our IDSS and people's response to it? Next slide, please. First thing to note, that's the Cat 5 storm sitting over the Bahamas. Look how close it is to Miami. Didn't evacuate. Hundreds of millions of dollars saved, folks. But more, as importantly, the systematic then evacuation up the coast based on the forecast, based on the IDSS, based on a trusted relationship, minimized the number of people that had to be evacuated and didn't cause those traffic jams. All right. So, and it was, again, we're seeing this now over and over again. We're not seeing any lives lost or very few lives lost to storm surge when that used to be the maximum death threat, you know, in these storms. Okay, next slide, please. So we got this fire situation in the western third of our country, and we really resonate with what Australia was showing. And we have partnerships with them where we send people down to help. You know, we have, you know, when we have a fire season that actually ends, we can help you know our brothers and sisters out down in Australia with respect to the fire situations down there. Got 93 glorious years with the IMETs, but they're on the fire lines. But there are things that are happening to fires. They're burning hotter, they're moving faster. And now the communities want to evacuate before the fire gets there, not when they see it coming over the hill. That doesn't work anymore. Think Paradise, California. They burn hotter, they move faster. You got to get them out of there so that the agencies can then focus on fighting fire. So let's go to the next slide, please, see what's going on in California. So in 2017-18, there were different protocols all over the state. They were really focused on evacuating when they could see the fire was actually going to hit the community. That didn't work very well with these new fires. You go to 2019, IDSS provided days in advance through governmental offices for a consistent response. They evacuated before the arrival, and the firefighters didn't have to worry about evacuation. They could fight the fire. They held the fire line. Similar kinds of things were happening with that Lake Tahoe, that city. They evacuated 20,000 people, got them out of there, held the fire line. They could focus on fighting the fire. Okay, next. So lessons learned, intergovernmental, it's across all governments. All right, that's what we have to do. That's accuracy and consistency. Water IDSS doesn't equal weather IDSS. Rural IDSS doesn't equal urban IDSS. You got much more preparedness and ability to shelter in the urban environment. Rural areas, poor areas, not so much. So where do people go? All right. So we have, you know, these issues are being worked. at the state and local levels. The user demands for accuracy, consistency in our products and services to facilitate decision making. They are asking for that longer lead times when forecasts are more uncertain. So this is opening up a whole new science, this deep uncertainty. How do you get people to react properly when you have this level of uncertainty? Okay. And then successful IDSS is a function of physical and social sciences working together. I can't get into much detail on that. Next slide, please. But it is true, and we are bringing more social scientists into the weather service. So really briefly on social equity, this is a nice diagram which shows what social equity actually is. It's not equality, it's equity. You have to provide a better foundations for the underserved. For example, if they speak a different language, right? If they don't have access to all the products that we have because they don't have the connectivity, et cetera, et cetera. So there are things that have to be done from an infrastructure point of view to really address the equity issues. Next slide, please. We are making progress in the Weather Service. We have an incredible reputation in working with the tribal nations, the urban and rural poorer populations, where we're in the process of addressing that. Spanish-speaking communities, translating our products and services into Spanish. In the Southwest Pacific Islands, we're hiring people now. We've been training people, educating them over the last 20 years. We're actually hiring the people from those islands that have that community connection, because that trusted relationship is facilitated by that. And in Native Alaskan communities, we're taking the same approach now and really adjusting what we do by listening to their needs as their traditional knowledge is being undermined by the climate change. They really need us more. So all of this is ongoing through different parts of the United States, but we have a lot more to do because we have a situation in the United States, especially in the urban areas, where racial mapping, go to the next slide, please, where racial mapping has actually led to areas, and this racial mapping and this red line districting actually happened in the 1930s, but we're still seeing the effects of these because they don't plant trees, they have more blacktop, they don't paint the roofs white, et cetera, et cetera. We're seeing areas of the cities that are 6 degrees hotter than the surrounding areas in the city, not the suburban areas, okay? That's life-threatening, even in a normal heat wave now. This is life-threatening. So these needs for the urban IDSS are more complex and require focusing on individual neighborhoods, addressing community needs like heat waves, air pollution, urban flooding, and major snowstorms. And so we're in a process of identifying these vulnerable areas across the United States. Next slide, please. And this is the last, if you can hit the next button, this is the last thing I'd like to present. We have introduced a dynamic water model that's now a basis for our hydrological predictions, working with the 13 river forecast centers. So this is something that we've introduced over the last 4 or 5 years. You can see the output points and everything. So from a science modeling perspective, we are working with the community in not only introducing this model, but enhancing it to higher and higher resolution. But it's more than just the modeling, and it's more than just the forecasting. Again, it's getting, mapping this and getting it to decision making. And I'll just show you 2 examples. Next slide, please. On the left-hand side, this is a 5-day forecast, which shows a flooded river in New England. This was up in New Hampshire. And that little square in there was really important because the locals knew that it was in that area that they were setting up the tents for COVID testing. We gave them a 5-day forecast and said, maybe you don't want to set up that test in that particular square, in that area, because you're going to be underwater. They didn't set up their tent. And we got a big thank you for that, okay? So that's a mapping thing that we're now doing, not only in New England and Texas, but we're spreading that across the United States. And then with this Sentinel synthetic aperture radar device, we can actually start seeing these ice jams and ice breakup, which are critical to the Native Alaskans. So we get this material, we have our forecast, we listen to the elders, we present this, they like it, we work with them so that they have a better understanding and that we get it to the right people at the right time. So these are the kinds of things that are going on in the water program. All right, next, please. So In summary, the magnitude of change associated with weather radiation is enormous. Our job doesn't end with the forecast and warning. We must connect to the intergovernmental levels. We must sustain our local presence. This part of our mission does not lend itself to centralization, folks. Maybe the numerical modeling does, but this doesn't. You've got to have that local presence to make this work. The success stories abound through the U.S., and we review this every morning as part of our stand-up. This is happening every day. We can achieve our mission without this, but there's more for us to do to address the social service equity and to support the weather-ready nation, not only in the United States, but we're doing this internationally now too, especially in the Caribbean and Southeast Asia. And there's some really big success stories that are already happening through the interactions between those weather services and their emergency management community. Okay, next slide, please. So all this, we wrote this up in the 2019 BAMs. It's available, obviously, and certainly addresses it in more detail than what I was able to do here. And I thank you very much for your attention.
All right. Okay. Thank you very much, Dr. Isolini. And so we welcome all the questions. Ask you to put your questions in the chat box, and we are going to have the speakers answer the questions at the discussion time. So let's now move to our third speaker, Dr. Gabriel Herger. Dr. Gabriel Herger, of course, is a very famous climate scientist specialized in extreme climate extreme research. And he has a very distinguished career and has many honors, including being the fellow of AGU and AMS and Royal Society of Edinburgh, and also a fellow of the Royal Society. So let's welcome Dr. Herger to talk about recent extreme events different from those in the past. All right, so Gabby, it's your platform. Take over.
Okay, thank you. It's a great honor to speak here, and it's a hard act to follow the previous two excellent talks. And I'm going to on a slightly different track. I'm going for looking at some old extremes that occurred in the past, and I'm trying to persuade you that there's a lot of interesting insights from looking exactly at what made past extremes so extremes. And I would like to acknowledge a lot of my co-authors, some excellent postdocs and collaborators that did the actual work on this talk. So I think Pandora has given us a great rundown of recent extreme events in Australia. And we had also this year some very spectacular extreme events, particularly extreme heat in both in the heat wave in the Pacific Northwest, which was not record breaking but record shattering, and also at the same time some very extreme temperatures in Jacobabad in Pakistan. So where the temperatures were approaching lethal levels to humans, which is a scary idea. So so heat waves have been very dramatic recently, but we had some interesting and strong old hot events, and there is some interesting lessons to be learned from them. And so the first one and the main one I'm going to focus in this talk is the heat waves in the US Dust Bowl. So in the 1930s, there was a lot of iconic photos from that period. It was a very interesting period when the Great Plains were opened up for agriculture, were plowed up, and initially produced a lot of wheat, and that got very good prices in the 20s. And then after the economic crash, and also after oversupply of wheat, and the wheat price dropped quite dramatically, and the farmers tried to adapt to that by just planting more wheat. So there was a dramatic expansion of cropland, in replacing the prairie, and in the 1930s also a drought settled in, which then which then really impacted the wheat production and impacted the vegetation, and caused the production to drop, and farmers went broke, and a lot of migration occurred, and very famous novels were written about it, like Grapes of Wrath, and so it was a very dramatic period. There were also dust storms. Kids died of dust pneumonia, and it was a big societal upheaval. What was also interesting, what struck me when I looked, when I was still living in the US, when I looked at extreme events and extreme temperatures, was that these periods had very extreme temperatures. And you can see that in today's maps, when you look at a map of trends in the number of warm days, and you look at the Great Plains, it looks almost like there is no trend. And that is largely coincides with the fact that such a very strong events occurred early in the century. So to bring it into context, one factor that we have to consider is that it was a very dry period. So there's a lot of papers written about the drought in the 1930s, particularly by Ed Cook and collaborators. And it was one of the two strongest droughts in the 20th century, so peaking in July 1934, which was also happened to be a very hot period, the drought then was more widespread than the drought in the 1950s. And so these were quite extreme droughts in the context of the 20th century, but it is worth remembering that there were some very strong droughts are seen in reconstructions of the last millenniums that make these the 20th century droughts look very weak. So there's potential, and there is uncertainty, of course, in reconstructing drought from treating data, but I don't think that uncertainty is large enough to not understand that there were some very extreme droughts that overshadowed these earlier in the millennium, particularly in the first half of the millennium. So it was a dry period, and it was also a very hot period. And so when you look at that graph on the right-hand side, you can, that's the daily maximum temperature in red, and the daily and the annual maximum daily minimum temperature. So basically you pick all the nighttime minima in the year, find the hottest one, and then make a plot, or the hottest daytime maximum in a year. And when you plot those two on top of each other, you can see that both the nighttime minima and the daytime maxima were hottest in the 1930s over the Great Plains. So particularly striking 1931, 34, and 36 heat waves. And so that is the reason why the plot before showed no trend over the central US, because the record is dominated by these very hot extremes. This has also not been lost on the more skeptical voices on climate change, that there has been a very extreme heat events very early on. And it also makes it quite, it's quite an anomaly in many regions when you look at hot extreme temperatures, because over most regions you see the most extreme events now. So it struck us as very interesting to analyze and try to find out what actually contributed here. And before I go to what we found, I would like to just briefly say we looked at a few indices of how to characterize a heat wave. You can do this in lots of different ways. You can look at the amplitude, the hottest day of the hottest summer event, the amplitude of a heat wave. You can look at the frequency of heat waves in a summer, how many days are under heat wave conditions. You can look at the duration of a heat wave, what is the longest summer heat wave, and you have to decide what is a heat wave. And in our case, that's a quite widespread way to go about it. You look at the 90th percentile of your of days around your calendar day. So what is a quite warm, let's say 10th of June, compared to the 30 years around you, for example, and then you decide that something is in heat wave conditions if it's above the 90th percentile for 3 days in a row, and possibly also 2 nights in a row. So you find those heat waves and then try to figure out what makes them strong. And I could see in the chat before there was a question about soil moisture preconditioning, and that is one thing that matters really in this Great Plains in the US. So that's a very complicated graph, but if you focus on the left-hand side, precipitation index, the SPI, which looks at precipitation anomalies, and we have classed the heat events into those following wet versus dry springs. So the 10 wettest springs in the 20th century, 10 driest springs, and then the big blob is their mean. And you can see that, for example, the number of heat wave events in a summer is the really high numbers of events are much higher up if they are an orange dot, which is a summer following a dry spring as opposed to a wet spring. And that it makes a lot of sense because it is much harder to warm up strongly when you're still busily evaporating moisture from your soil. And it's quite a few regions on the planet where this matters. It doesn't really matter in high latitudes where it's very hard to dry up the soil, and it doesn't matter so much in very low latitudes, but in, for example, the central US or also southeastern Europe, it matters, and you can see a real difference in heat wave activity following dry springs. And you can see that this is the duration is longer, the amplitude is stronger, and significantly so if you follow a dry spring from data of the 20th century. So it did matter, and it made it easier to get these very hot heat waves because they were in a period of decadal drought. Nevertheless, you would think that if you run a lot of climate models with reasonably realistic conditions, you would think that some of them would pick up such hot extremes. But if you look at this graph here on the top, the gray shade is the CMIP5, so that's the previous modeling exercise. I would be surprised if CMIP6 does something not dramatically different over the Great Plains. So the gray shade gives you an idea of what the anomalies of the annual maximum temperature are in a lot of climate models. And you can see that it's meanders around over the 20th century and has a tendency to slightly go up. And definitely, but none of these runs hits the extremes that we have actually observed in the 1930s. You can look a little bit at climate models in control mode, where you can run them for extended periods of time and see and let the weather vary and see what kind of heat you can get if you look for the rarest events. And then you can see that in the observations we had, these kind of strong events coincided with the cold North Pacific and quite a warm spell of the Atlantic. Part of the early 20th century warming was quite strong warmth in the North Atlantic. And and just by chance, there's one simulation in one model, in the GFDL model, that happened to have a warm blob and a cold blob here, and also happened to have quite strong heat wave activity. So what I'm saying with that, with this long-winded explanation, is that if you have exactly the right things in place, the right sea surface temperatures that make drought more likely, then you might, under very rare conditions, get heat waves such as observed or similar to those observed, but it's still quite hard to get there, as you can see with those climate models that never quite reached there. So something else must be going on. And that something else is probably the devegetation. So we did a whole lot of climate model simulations. The top row gives you ones where we made the Atlantic or the Pacific to the observed, turned it to the observed sea surface temperatures, and the other ocean basin to climatological conditions to see which one is more important, and which tendentially suggested that the Atlantic was particularly important for the heat. But what the other experiment that was particularly striking was if we started to devegetate the surface and increased bare soil by 30 and 50%, you get all of a sudden a dramatic increase in heat wave activity. So you get a lot more days of heat wave conditions. So here under 50% bare soil, you get a really strong, super significant increase in the number of hot days if you devegetate, which has been observed at the time. There were reports about land degradation, and so this is probably was a big factor in driving heat up to such extreme levels. So if you do 30% increase, you don't see so much, but with 50, you get a quite dramatic change. And if you look at what happened, it's not so much that you reduce precipitation. There's maybe a slight tendency in the devegetated experiments, which are pink and red, compared to the control experiments, which are gray. But you can see that the evaporative fraction over the late spring and early summer is much, much lower in the vegetated experiments, indicating that there is not enough moisture available for evaporation. So in those, so that model and similar work has found in other regions or in or also on the Dust Bowl with different models has also suggested that this was a really big factor, that the devegetation connected to the agriculture and then the die-off of the cropland contributed to making the heat waves so intense. And then we played a little bit with what would happen if we would have something like this today, if you would have conditions like we had in the 1930s, the drought conditions and strong heat waves. What would happen if we had those today? So this is the station data records again for heat wave frequency. And then we had a very, very large ensemble of climate model simulations run in Oxford. And here are the 10% strongest heat wave simulations that reasonably reproduced strong heat wave activity. If we change greenhouse gases from pre-industrial to the 1930s conditions, you get a slight increase in heat wave activity, but more so in the east and towards the Rockies than actually in the Great Plains themselves. So at the time, there might have been even then a small contribution by greenhouse gases. And there definitely was a contribution by greenhouse gases to the strong early 20th century global warming, but maybe not as large, not so much to these particular heat wave conditions. And then if you go ahead and increase greenhouse gases some more to the atmospheric greenhouse gases of today, but the same sea surface temperature conditions, then you see quite a strong increase in heat wave frequency. And if you then go ahead and further increase the conditions of the sea surface temperature also to the present day conditions, then you get heat waves of the extent of the early of the 1930s heat waves. I mean, in this case, 1936, much more frequently than you get today. And if you are a fan of these return period diagrams that the extreme weather attribution community does, you can actually follow this up as if you look at the 1930s conditions. This is basically the return period of a summer heat wave frequency here in days as observed in 1936. So there's an uncertainty in the data captured by this bar. And then, for example, if you go for the lower end of the bar, you wind up with about a 1 in 100-year return period of those heat waves, which I think is an underestimate. And there's a long explanation why it is, because it includes the event itself. But if you if you then go ahead and increase greenhouse gases to present day, you wind up with a 1 in 40 years. These two things are then strictly comparable because we are looking at the same kind of thing. And then if you go and use the 2015 sea surface temperatures on top of that, which are not exactly a match, but similar enough in terms of Pacific and Atlantic, then you wind up with a 1 in 15-year event. So in other words, if we had the same conditions, the same event would today be hotter, which is not super surprising, but nice to quantify. And so this particular heat wave event was probably very strongly influenced by the devegetation. And if we disregard the devegetation for a moment, just based on the meteorology, we would get it, of course, hotter if it came today. We work with other early examples. So in the moment we look at the 1911 heat wave in England, which some of the early heat waves in station data are actually surprisingly hot. And even though the monthly temperatures show a strong global warming signal, you get some quite interesting early events to analyze. And so we find old extremes useful to analyze because despite climate change strengthening events, some old extremes are really strong due to rare conditions. And so if you look at these rare conditions and plant them into the present time or the future, you get a sense of what a strong event could look like in the future. But what is particularly important to me when analyzing them is that you see some feedbacks in the systems that the coupled models don't always include. So for example, the vegetation lost for the dust bowl and the dust storms, which I think the newer models can actually do spontaneously, but the old models, you would have to import the dust. Or you can get societal responses that exacerbate conditions or impact what happened. So in that case, the very, very rapid change in land surface from prairie to cropland, and then the societal response. So these extreme heat waves in the past were also exacerbated by the response of vegetation and of society, and this is not something we are doing very well yet in our model predictions. So there is a danger that we underestimate some of the extreme events that we might see. I mean, we could also think about fires, for example, irreversibly changing the forest cover, or and we are only now starting to seriously analyze what could these feedbacks be and how could they happen in the future. And if I still have a few minutes, I'm going to look at future extremes, which looks at the risk of a presently 1 in 10 years hot extreme in a world that's 1.5 or 2 degrees warmer than pre-industrial, and then 3 degrees as a comparison set. And so this is a plot that shows you how much more frequent is a 1 in 10 year event at 1.5, 2, and 3 degrees in worldwide, based on the new model experiments, CMIP 6, and this is based on a few models with very large ensembles. And you can see that under 1.5 degrees, which is the Paris target, we would see that an event that presently occurs once in a decade, it would occur maybe would have a risk ratio of about 5 or so. So it could be up to every other year or so in some regions in the tropics. You can see that this change is much more dramatic in the tropics, where the variability is a little bit lower. So you can see a stronger effect of warming. And if you go to 3 degrees, which is what we really want to avoid, then you wind up with a 1 in 10 year event every year or so. When you do this, it's interesting to look at some regions where the extremes change a bit differently from the mean. And so we have looked a little bit at a very ice-covered region, Svalbard, and then the Amazon, where in some models you get a significant broadening of the distribution, where the hot extremes change more than you would expect from the mean. Also Southwest Australia, Central Europe. And the first lesson is that compared to the reanalysis in gray bars, the climate model extreme value distributions that capture approximately what today's extremes look like in the climate model don't do so well. For example, for Svalbard, they underestimate, the models we used underestimate the hottest day in a year by quite a bit. And then all models tend to make it a bit narrower. So they tend to say that as we lose ice cover, we get the distribution of the hottest day gets a bit narrower and steeper. So you don't widen out the tail so much. But on the other hand, if you go for the Amazon, for example, some models really widen out your distributions very strongly, consistent with losing vegetation cover and drying out of land and getting very, very hot extremes. So there's a lot of questions still about how well models do extreme events into the future, and how that behavior in the future is connected to how well they do in reproducing them today. So my question was, are recent extremes different from the past? And I would like to answer that there are actually surprisingly large extremes in past record, not only hot, but also wet and dry. And some of these may well be accurately measured. It's easy to suspect the data when it's an old event, but some of them might actually be quite realistic. And but of course, on the other hand, we are shattering records left, right, and center. The temperatures are clearly going up, and hot and very wet extremes are being broken everywhere. But among those, we have to not only think about a slowly moving distribution that is shifting towards hotter and wetter, but we have to think about to what extent we arrive at dangerous conditions. So where we arrive at thresholds that are dangerous to humans, and how this might affect society and vegetation and ecosystems. But these rare old extremes tell us what kind of conditions would lead to very, very extreme events, and they can tell us what feedbacks can happen that we might not anticipate. So I think old extremes, recent extremes, are different from past ones, but the past ones have really nice and useful lessons for the future. And I think with that, I would stop.
All right. Thank you very much. You know, we have three very exciting talk, and Dr. Pandora Hope talk about the extreme events in Australia, and also, you know, they use their scientific understanding to forecast those kind of extreme events. And Dr. Usanidi talk about the weather ready nation, you know, the program, a historical perspective about, you know, the achievements in the U.S. And also Dr. Hegel talk about, you know, they give a historic perspective on those different events, different extreme events. So now we are going to have the discussion session. I'm going to turn over to Dr. Ariel Dinar. He is going to moderate the discussion session. I noticed these are the questions. So is Ariel ready? All right. Okay. So
very much, and we have a discussion section that will be motivated by some of the questions that already have been recorded. Let me just say a couple of introductory words. So I was really impressed by the capacity of the science to predict, also in some slides of both of Dr. Hope and Dr. Hegel, there was a statement that we are still not sure about the quality of our science models. And then I was also very much impressed by the presentation by Dr. Ussellini about the nation readiness and preparation for extreme events. By the way, I am a big fan of the national weather temperature forecast that I use for making decisions how to irrigate my my yard. So I have developed some good, in my opinion, good decision-making tools to decide how much time to irrigate when the forecasted temperature is such and such. So thank you for doing that service. So why don't we start with, in order, with the questions that were posted. Some of them were already answered, but I will let the speakers answer them now verbally. So the first set of questions were for Dr. Hope, and the first question is for Catherine Vaman, if I'm pronouncing right the last name. Do you have reforestation programs in strategic areas, and what is your opinion on this?
Thanks for the question. I don't actually know about this across Australia, but what I do know following fires, our vegetation is actually evolved to really respond well to fire usually. And it's a common part of the landscape, and usually you get excellent regrowth after a fire's been through. But unfortunately, with the 2019-2020 fires, some of them were so extreme that they actually killed the trees. And so I do think some reforestation programs might be useful, but obviously with COVID, we've had rolling lockdowns across parts of the country. And so I'm not really sure how much effort has been going into that recovery process. I certainly haven't been able to drive out into those areas or really very far. I'm in a 5-kilometre lockdown at the moment. So, but yeah, I think we perhaps need to think a bit more about the recovery efforts, because in the past, the fires were less severe generally and didn't kill the trees, and they would recover on their own. So it's a really good question.
Yeah. Okay. So the second,
if you want me to, I can also add something to the trees because it's a hot topic also in Scotland, because we also because the trees would take carbon out of the atmosphere. So they affect the climate, and that can be really a good moderating effect. And there seem to be studies looking at urban areas, for example, more leafy and less tree-covered areas having hot, really being good in moderating extreme temperatures in urban areas. On the other hand, for example, in Scotland, planting trees on peatland has a net negative benefit on carbon, because peatland stores so much. So it's a tricky area, and it's societally really interesting, because there are some people having very strong feelings about tree planting, and I wish it was the solution to everything, but I don't think it is. But it could be really beneficial to moderate the. But as Pandora said, if your trees burn, then it doesn't help.
Yeah.
No, it doesn't help. And in Australia, we don't have a lot of water generally. And planting trees is sometimes not a solution in some areas where they don't usually grow because they won't have enough water.
Yes, that's correct. So let's move to the next question to Dr. Hope. And this was a question from Muhammad Umbadi. And actually, there are two questions. So the first question is the following. You hinted at potential impact of unprecedented soil moisture conditions in both flood and drought events. Would it be possible to carry out a formal modeling attribution analysis of such hypothesis?
I think it would definitely be something that you could examine. You know, certainly if you just think about it in terms of what you might expect, you would sort of see that this would be the case. And our efforts in that examination of the fire sites and the leading in of the soil moisture to those fires, I think I was surprised that hadn't been done very much before. We had a cross-disciplinary team, so we had people from the sort of weather community that were good at modelling the fires. We had climatologists that were good at looking at longer records, and we had land surface modellers and hydrologists, as well as people who were good at understanding the ecosystem and physiological changes of the trees. And we came together, and I think that's just the sort of team that you need to address this kind of question. In terms of formal modelling attribution, I think some of the points that Gabby pointed out about the limitations of the climate models in some cases to actually have that good connection between the atmosphere and the land surface might limit some of the efforts there. I don't know if Gabby, if you'd like to add a bit to that.
Yeah.
Sure.
So,
it would be, I think it would be really interesting, for example, to look at what the speaker mentioned. I think is wet wet events on wet soil. So that is something that leads to very extreme flooding. And I think that's an area where I would feel a bit more confidence in the models. And the preconditioning for dry soils, I think that is something that is really interesting, and we have to really work hard on getting the models, evaluating the models before we use them. But there's definitely interesting things happening, and we have looked a little bit at what, for example, if a model dries out the soil too much in the present day conditions, which a lot of models do, you might actually underestimate how much more hotter it gets in the future in some regions. So it's so there is, yeah, as Pandora said, the model difficulties are what is becoming particularly important when you look at events that impact stronger on humans, that breach thresholds. When you care about a threshold, a physiological threshold of like a wet bulb temperature of 35 degrees, then you really want your model to have a reasonable climatology, which is something that is more challenging than you would think. So I think our applications to looking at real dangers associated with climate change really challenge the models, and we still have work to do, but they are getting better. I think they're getting better. Pandora, would you think?
I do think they're getting better. Absolutely. There's so much more consideration about that coupling between the atmosphere and the land surface, and a lot of effort's been going into that. Certainly, your point about being able to do it actually reasonably well. I have a little study I did years ago looking at the ameliorating effect on heat extremes from saturated soils. And so just looking in the observations and the persistence of a very wet month forward in time and how that impacts on maximum and minimum temperatures. And the models actually captured that signal really well. So yeah, that's a good point.
If I could add something here, I really appreciate the conversation and the implications for the longer timescales. One of the critical problems we're facing now from a forecast perspective, which gets us into that zone between weather from week 2 out to the subseasonal, we have seen what is now being termed flash droughts develop in about 4 to 5 weeks and take a corn crop over an area the size of a state or larger that look good, and with projections of, doing really well the rest of the year, go absolutely black within 5 weeks. And the science, the folks who are working the science of this are saying that it has, well, let's put it this way: the hypothesis that they're working towards is the soil moisture, and whether they had that right in the models in the first place, and the short-term response to that, right? That then feeds back, because once you start the cycle, the ridge builds as well in the atmosphere, and then you start getting this compression, under the ridge, and it just sort of feeds on itself. It might tie back to the same deficiencies that you're pointing to for even the longer projections. And I thought I would just note that we have a lot of interested senators who want us to focus on flash droughts. So I'm just pointing that out. Thank you.
Yeah, we've been looking at flash drought quite a bit in Australia, actually from the speed with which you can destock if you're feed. If you've got sort of, free roaming cows and the grass is not going to survive the coming sort of heat and dry, and how quickly can you get your cows off those paddocks? Yeah, it's a really interesting question, which actually that evaporative stress index that I mentioned in my presentation is used as an indicator of that, but they don't have a soil moisture component to it yet.
Thank you very much. I would like to actually ask a question that was, I planned to ask that question to Dr. Hope, but I saw that she placed that question already to Dr. Usilini. So I wanted to ask, in Australia, what we saw recently are extremes of very hot weather that ended up in wildfires and floods, and affecting differently or to different extent different communities. So what I wanted to ask is whether or not Australia has also a program of community preparedness, and how does it work, if it does work? If you can talk about that, this will be a nice move to the next presentation by Dr. Ursellini.
Yeah, I was really impressed with your presentation, Dr. Ursellini. I think it was a really nice example of that kind of local connection that you can get with the forecasters working with the community, and I'd love to see more of that in Australia. Certainly for us, we have, as I mentioned, a national broadcaster on the radio, and they were well briefed in the seasons leading up to the fires about where we felt the fires might actually occur and where they needed to actually build expertise and training of their staff and deploy them earlier in the season. And so all of that happened in good time. And often as fires rage through a region, you lose contact on any telephones, and radio is the only way to reach communities in that sort of very intense period where they're looking to evacuate, and which roads are open, which are not. And I think that was handled quite well, and that also goes out to all the emergency services. So we actually, we have this ready, set, go system where we have the seasonal forecast going out and a lot of conversations with those sectors.
So the question that Dr. Hope put for Dr. Ursellini is, do you use input from the seasonal to multi-week forecast for the decision support system? And then she mentioned in Australia, we have a ready, set, go system using a seasonal forecast. So if you can.
So the answer is it depends. For water resource managers, well, first of all, we run a seamless suite of model products, which are now dominated by multi-model ensembles, from the very short range for, let's say, severe convection, that kind of thing, through the weather domain space all the way out through 2 weeks, to the week 3 and 4, that no man's land, as some people refer to it, between the weather and climate communities, to subseasonal to seasonal. And we run those every day. We find that there are forecast requirements in the water resource management that really focus on the seasonal to subseasonal, and then as you work your way down. So, and especially if we have, forecast out that those seasonal models do influence with respect to ENSO, the western third of the country will prepare accordingly. Now, how that forecast for the precipitation is realized is complicated, as we see. It's not just flow off the Pacific, but it involves cross-polar flow and everything else. So, but those forecasts are made and are demanded more by the water resource folks that we work with than anybody else. We're also starting to see now, so it's this requirement basis of 30 days and beyond. So the management of the rivers, those folks who do that ask for forecasts of precipitation out to 30 days. The resource managers in the western third of the country will look into the seasonal range. What we're seeing now with the Arctic, having this variable ice cover, much more so than they did in the past, we're seeing ice forecast requirements that extend into the months, all right? All this is pointing to not just a seamless suite of models, but an interdisciplinary Earth system science approach. It's absolutely essential for us to embrace that as we move forward. And that's exactly what we're doing. That's what we're attempting to do, where we're pulling land, the cryosphere, atmosphere, and oceans together into one modeling system with interactive coupling. And some of the climate models are already doing that. The Earth system science approach. We got a lot to learn from them, to make that work on a daily basis, because we're seeing that there's even cases of the short range weather that's affected by that. And the last thing I'll note is that with space weather, we have what we call the whole atmosphere model now that goes all the way up to 600 kilometers. You say, why do that, right? Well, that environment in a space weather event is influenced by the upwelling gravity wave modes that can affect the response all then of the space weather event down to the Earth's surface. But there's evidence that the stratosphere itself, these sudden stratospheric warmings that influence a 2-week forecast, for example, is influenced from aloft. So we expect to see a terrestrial weather, improvement from that in a space. It really just points to this whole new era of this interdisciplinary sciences driving our modeling systems from short range all the way out to the subseasonal, the seasonal range in a much more effective way. So we're in on that, and there are a large group of users that rely on that whole time zone, that time advance right into the events themselves. So the answer is yes.
Okay, thank you. So another interesting question is how can you forecast fires with these models? And the question is based on soil moisture?
So that was really, I guess, the...
This is for Dr. Uccellini, but anyone who wants to answer.
Okay, so could you repeat that question?
So could you forecast fires with these models based on soil moisture?
Yeah, so the fire weather and the watches and warnings that are associated with that are driven in part by the atmospheric conditions, especially wind, temperature, and dryness, but also on the fuel source. So, what is the characteristics of the fuels of the trees? So if we've had an extremely hot and dry 1 or 2 weeks, those on top of a long-term drought, it really drives the fuel part of the equation as well. We don't predict fire behavior. There are other agencies now that are doing that modeling and will do it. There is some talk about how we should be running those models especially for the short-term prediction. The other thing we do, I should note, is that as soon as the fire is out or is under control, we use satellite data and we use on-the-site analysis to study the impact of the fire on the soils, because one of the big risks is a big rain event, within months or even out to a year over that same area. And we get something that's called a debris flow. The whole earth basically loses its infrastructure. So you're not just getting a flash flood, you're getting boulders coming through your house. You're getting a house filling up with mud in less than 5 seconds. Okay, these things are extremely dangerous. They can be forecast, like if you have a certain amount of rain. So that IDSS is working with local neighborhoods to be on alert. If we're forecasting this amount of rain, local officials will go out there and want you to evacuate before the flooding starts, because the damage from that happens so quickly. All right. So all of these things before, during, and after the fires are being looked at for modeling, et cetera, from an Earth system science approach. But we're working with what we have now to get people ready and responsive to the fire, and also be ready for the danger after the fire from these debris flow type flash floods.
Thank you. And Dr. Hegrel, if you wanted to also add to that question, please do so. I'm sorry.
I think Pandora knows more about fires than me, but generally, I think there is a individually and for a specific region, it's really hard. But generally, if it's hotter, then you increase the fire danger just because you evaporate more.
Yeah. Thank you. A very interesting observation also to Dr. Uccellini by Gilbert. So first of all, if this is true, and if is it true, then what makes Africa to be less prone to wildfires?
Luis, you're muted.
You're still muted.
You are muted, Dr. Russellini, you are muted. Please.
Yeah, I know. I think somebody was interfering at the
Yes.
same time that I was unmuting.
Sorry
So-
about that. My apologies. I was going to ask you right when you did it.
Hey, listen, I fat finger one machine after another, so I am really conscious of this. There are parts of Africa that do experience fires in those transition zones between the deserts and the wetter areas. I think part of the reason is just that there is currently, especially the equatorial parts, that you'll see that water reservoir in the soils and the trees basically are sustained during the hottest part. And so you have to have that right combination, right? Of now we've grown this fuel in the western third of the country. We've been under a drought ridge condition basically for the last 5 years. We've had the beetles, these bark beetles decimate miles and miles and miles of woodlands. And that's why I think these fires are burning hotter and faster, because we're talking about hundreds of thousands, millions of trees actually now that are dead. The fire gets going and that burns hotter and it advances faster. And then you just throw a wind on it, boom. So all of these things are combining to bring the fires in a rage, actually. Now, the fuel, the prolonged drought and heat, the infestation that's been going on for the last 10, 15 years now, probably related to global change, because these beetles don't get killed off in the winter anymore. All of these things have combined in the United States. So in Africa, I would suspect that the water part of the equation is still significantly in a positive range to prevent that from happening up to this point. But in the fringe zones, you are seeing fires.
Yeah, thank you. Thank you very much. Let's move to a question that was about Dr. Hegrel presentation, and it was answered, but for the sake of the remaining audience, I will just ask the question and you can answer it, please. So what are the characteristics of vegetation that reduce heat wave impact? Is there a significant difference in the type of vegetation that is lost? For example, forest versus grasslands.
So if you lose your grass cover, or then you just hang on to the soil much less successfully, so the soil dries out quicker, and you can have and the energy from the sun is used to heat up the air rather than evaporate the moisture. So you get hotter conditions. But then, of course, locally, the vegetation also can really influence the microclimate. You can keep it cooler with shadow and a shade. And so it's a complicated interaction. And I think one that we are still trying to we should use a bit better when we adapt to climate change, I think. And there's maybe also some opportunities to mediate some of the very strong, very extreme heat that is coming our way. But then, of course, if we burn down those trees in fires that also link to climate change, that's quite scary. And with the US Western fires, I'm always struck that there was a report by the National Academies, I think, that came out in around 2010 or so, America's Climate Choices, and that said that fires in the West are one of the first things that will emerge from variability. So it's really come to pass. So I think we need to be really concerned about adapting and also addressing this issue.
Could I add on to your microclimate comment?
Yeah.
That example I showed in Baltimore, that was the front page of Baltimore. There's a correlation for that area that's 6 degrees hotter than the rest of the city. There's something they call the Red Line District, which was established in 1938. It's where the African Americans lived. And so there was really very few infrastructure changes there. No trees planted, You know, the roads are paved with blacktop, all of that. The rest of the city, you can actually see the correlation. The rest of the city that has the tree cover, especially away from the taller buildings and areas where people are living, are 6 degrees cooler. And that 6 degrees in a lot of cases is the difference between a heat wave and an extreme heat wave. You know, they have all these life-threatening. And so the effort is, one of the first steps they want to do is plant more trees in those specific areas. Now, clearly, we have other infrastructure issues, like we don't have it really observed well, right? So we're working with the city now to try to get more observations into those areas. Other people, nonprofits, are working on in other areas. So, but that was one of the really interesting things about it, was just you can even see it on the map, just the lack of trees. You know, over the past 80 years, nobody invested in that part of the city, even from planting trees.
Yeah, that's a very real observation. And we know that also, you know, there are studies on Los Angeles of different microclimates with correlation to vegetation. So in the interest of time, I would like to combine all the remaining 3 questions that were asked to all the speakers, and because they are very similar, and you can respond to them. So question from Catherine Weyman about increasing vegetation. If increasing vegetation cover and reforestation could help change climate events or reduce extreme events. So you, Dr. Uccellini, you already gave some kind of an answer to that. So this is one question. Second question is, if nothing is done about climate change, what is likely to happen and how soon? And this probably will take a lot of courage to answer. And the last question is on extreme weather events. We have seen an increase in frequency and severity. Do we foresee a stabilization point in the future, or the situation will continue to worsen by the day or by the year? And this was from.
Well, I'll jump in as the weather guy here. I think we're on the, I read the IPCC report. Basically, this report's different, right? They took the gloves off with respect to the linkage between extreme weather and water events and the climate change. People danced around that. You don't have enough data. You know, they took the gloves off and pointed to that linkage and that it's going to get worse. And I believe it. I think the fires are sort of the canary in the coal mine here with respect to it. But we've been seeing this up in Alaska for the past 10 years. You know, all the traditional knowledge about the ice and what happens to the ice shields and where the walruses will be and all that. There's no ice. Okay. At the time of the year that they would be congregating and that they would have the hunts, that's food for the whole year. Okay. So it's happening. It's happening before our eyes. People are seeing it on the coast. We're now seeing it inland. All right. And so I think it's for real. And I think this IPCC report needs to be looked at and considered very carefully, because it's different. And basically, you don't have to wait 20 years out or 100 years for and maybe that was the problem, was that everybody was thinking this was going to be 100 years out or 80 years out or whatever when they were first rolling out climate change. But it's happening in our lifetime and it's accelerating.
Yeah. Dr. Hope, Dr. Hegel, any responses to any of these questions?
Yeah, I think just following on from Louis, what we have in the atmosphere in terms of just greenhouse gases, it's really locked us in a continuing change for the next few decades. And obviously what we do right now is going to impact what happens after that. So Gabby and I showed those slides where you have sort of, those choices, 1.5 degrees, 2 degrees, 4 degrees warmer than where we were, and they have significantly different temperature and extremes. So yeah, it's pretty clear.
Yeah, maybe I can add the perspective that when I started my career, the goal of my postdoc years was to find the climate change signal in global mean temperature data. So basically you had to really aggregate your data to see if climate is changing significantly, and we did see that. And now, and it still seemed to be something that's far away and that you can see when you analyze lots of data in conjunction. But I think now it's really quite blindingly obvious that we are getting you're getting events that we haven't seen before. We are breaking records. We have really different climates in lots of places. I've also been at a meeting where one of the Inuit nation, a woman was there mourning the loss of their hunting culture, and as Luis just said, that their inability to do things the way they used to do, and losing with it their cultural connection. So things are changing really quickly, and I'm quite concerned for the generation of our children, that if we don't address this, I think it's going to be very expensive and very dangerous. And I think we tend to but that might be my personal view, we tend to underestimate the risks with climate change and overestimate the dangers and the costs of mitigation, because we really need to put the costs of the climate changes that are coming our way on a sounder footing. And I think the IPCC report has started to do this very nicely. So there's a lot more on risk in this report than in previous reports. And I think we are really moving in an area where we can actually estimate what will happen, what are the dangers in the future. But there's still things that we might be surprised by. And that's what I'm most worried about, that something will happen that really changes very dramatically where we are going, that we get a massive melting event, or that for example, West Antarctic ice sheet goes quicker than we think, and then sea level will rise much faster. So these are all kind of possibilities that are not the most likely ones, but very, very dangerous ones. And so I think we need to really look carefully at what dangers could come our way. And I think it would be very risky to go on the 4-degree pathway. I hope very much for my children that we don't do this.
Okay. Thank you very much. So I don't see any additional questions from the audience. So I would refer now to the moderator to conclude the session, and then to our chair to say some closing words.
I think I will try to end our first and very successful. Thank you to the wonderful talks by our speakers and the excellent discourse and discussions. As someone who's been in the hydroclimate side of things for the past 30 years, and having been involved with a number of these international entities, such as the Global Energy Water Cycle Experiment, WCRP, WMO, which Gabby and Duan are now serving, I guess, on the GWEX panel. You know, this premise that hydrologic cycle was intensifying as a result of, warming back in the 1990s has been proven. And this IPCC report, as Louis nicely put it, has really brought quite a bit of focus on that connection. So the extremes are there. We have to sort of live with them. Louis nicely presented the success of the US in terms of getting the nation ready to deal with extreme events, particularly on the shorter time scales. But all of us have been involved, as I said, on the international. And this is a global problem. And the question, I guess, if I was to use my prerogative, is how much do agencies such as the WMO and others are doing to help other nations to bring up their standards in terms of being able to provide the predictions and the capabilities to deal with that, because you hear so many other areas that are highly affected by extreme events, particularly in the developing world. Of course, China has come a long way. They're very successful in developing their own unique tools. But are we doing enough? I think this is an important question that I guess we all have to address. And this is an international forum. I think our speakers would certainly have a role to play in this. Two other things, since you were talking about forest and the wildfires, I remember a very little probably known study that was done by the Agricultural Forest Service in Flagstaff, Arizona, and the University of Northern Arizona. There was a graph that is still in my memory very nicely that showed, based on proxy studies that was done of the past fires, I assume using training, I'm not a expert in the field, but they showed that from the time that the US moved to protecting the forests, obviously there was a huge drop in forest fires and wildfires, but then when they happened in a very extreme way. And they compared that to the past several hundred years prior to these, which were mostly caused by natural incidents. And those little fires really took care of much of the fuel. And as a result, the intensity of those fires were not that extensive. And last but not least, I have been impacted by all of this myself. About a month ago, I got a notice from our home insurance company that they're not going to renew our home policy because they consider my house to be in the wildfire area. So the past few weeks I've been hunting for another insurance company, and finally I got one. So you see, it goes everywhere, and I guess we are somehow one way or another affected by it. With that, I'd like to also bring your attention to our next two exciting webinars on the COVID and water. That will be on December 2nd. And the groundwater in mega cities, which is an important issue, will be on Monday, February 8th of 2022. With that, I thank everybody and appreciate the moderators, Juan and Ariel, for doing a great job. And Sherry, as always, thank you so much. And I wish you a very good day. I know Louis is going to be very busy because they've got another major storm, Nicholas, that is affecting the Gulf Coast of, or the coastal region of Texas and Louisiana. And I bet he has to get briefings and reports available to him. With that, thank you so much. And have a wonderful day.